people have to agree and to be registered. Okay. Okay, I think it's time to start this webinar. So, on behalf of CARE Laboratory and International Joint Laboratory LECZ CARE, I would like to warmly welcome all of you to this webinar that is presented by Frédéric Cazenave. I will, of course, let Frédéric to introduce himself in a few moments. This webinar has been also organized with the help of Dr. Zan. So please, Zan, would you like to say some words before Frédéric is starting to talk?
Yes. Thank you, everybody. Yeah, good afternoon. First, I would like to thank Frédéric to give the talk on focus on the radars and cell phone signals and at a fine scale. On behalf of Vietnamese side, that I would like to thank Mark and Frédéric to organize the webinar. You know, most of the participants come from the HMUT, University of Technology, and the other outside institute and university. Like you see, the Dr. Hong, the director of the CHIMET, and some professor from the Nong Lam University and University of Natural Resource and Environment of Ho Chi Minh City. Okay, thank you so much.
Thank you very much. So please, Frédéric, it's to you now to present us this interesting webinar. Thank you very much. See you very soon.
Okay. Good afternoon, everybody. I'm very pleased to be there with you. I would like to kindly thank Professor Dan and Dr. Decroat to invite me to present this webinar. Also the University of Technology of Ho Chi Minh. I would like also to thank you, all of you, to attend this webinar. What I will present you now will last at mostly 13 minutes. And probably most of the things I will present you are very well known by you, but things has to be rewrite again sometimes. So the subject of my webinar is polarimetric radar and cell phone signal as tool to analyze spatio-temporal variability of intense rainfall at fine scale. So I'm a research engineer at IRG, and my laboratory is EGE. Most of you know this laboratory. So just to present me, I've got a diploma in computing science and also a PhD in hydrometeorology. During my work life, I have spent a lot of time working on radar, different kind of frequency, and I have been developed radar and as an engineer and also as a manager. I have also been manager of environmental observatory. I have made a lot of training and for capacity building with partners, and also I have been project leader of different projects. The more important probably are the last one, the Rainfall at Bamako. Bamako, it's the capital of Mali in West Africa. And this project was funded by the World Bank and also funded by the Korea. And now we are on the project called Rainfall Cruise Bamako. It's also in Mali, and we have the funding from the cruise project. So I have spent around 11 years with partners in Africa, living in Africa, in different countries. And I have also get the opportunity to spend 2 years in Canada at the McGill University. And I hope I will be able to visit you for a couple of years in the near future. I hope so. Okay, so why do we need to study rain? Study the rain is a key factor for many things of the around the world, and one is the growth of the economy. Rain concerns rainfall farming, the water livestock in semi-arid region, but also it's very important to know the rain for hydroelectric power plants management. Rain could also be an hazard, and in this case I can think about freshwater availability and also health security with the different diseases, and you can get linked to water like malaria or cholera. And also when we think of rain, we can keep in mind that it could produce, when there is not enough rain, it could produce drought, but also something very concerning Ho Chi Minh, the city, is the floods. So during my past and current work, I try to contribute to the observation and the understanding of rainfall during 3 different topics. The first one is the observation and the characterization of the spatial and temporal variability of the rain. And the question I try to address is, what is the efficiency of the next band polarimetric radar to produce rainfall fields at fine and spatial and temporal scale? We talk about few minutes and around the kilometer square. The second topic is concerning vertical structure of the hydrometeor in the convective system. And the address question is, how can polarimetric radar can contribute to study microphysics of precipitation? And the last one concerns flood risk and alert. And the question is, what is the potential of mobile phone networks to precipitation estimation? And how can this information be used in an early warning system of flood? For the rest of this presentation, we'll focus on the first and the third point. And the second point could be the opportunity to make another webinar in the future. So for the first question, we will talk about quantitative precipitation estimation by radar. Sorry, and to address this question, I have developed a tool for research. This tool is an X-band radar, so this name is Export. And the frequency of this radar is 9.4 gigahertz. That means around 3 centimeters of wavelength. And it's a dual polarization radar. The transmit power is around 100 kilowatts. That means per channel, we transmit 50 kilowatts. So when we use a conventional radar, we send energy in the atmosphere, and this energy, most of the time in the horizontal direction, waves, is backscattered by the drop inside the volume of atmosphere hit by the wave, and this energy is acquired by the radar and is used to be converted in intensity of rain. When we talk about polarimetric radar, we had a second wave. It's a vertical wave, and we're going to take part that the shape of the raindrops could change depending on their diameter. And that means the H and V signal, so the vertical and the horizontal signal backscattering could be different. So this will produce a polarimetric parameter, and we're going to use this polarimetric parameter to correct attenuation, also to produce an accurate quantitative precipitation estimation. And we could also use this parameter for identification of the type of hydrometeor or non-hydrometeor. That means we can distinguish between meteorological scatter and non-meteorological scatter. You can see here on on the border of the slide, on the right side of the slide, a straight line is the images taken in Niger. And what you can see is a straight line, a big storm with a very high intensity. It's a orange color of a storm, cell storms. And the green color is linked to the stratiform part of the precipitation. So with a conventional radar, as I said before, we use horizontal reflectivity, and this information is linked directly to the concentration number and also to the size of the particles. When you add the polarimetry, that means you have a dual pole radar, then you will access to other parameters like the different reflectivity. In fact, it's a difference between the power signal you can get at the horizontal channel and the difference with the vertical channel. And this information give you, this parameter give you information concerning the shape, and so the axis ratio of the particle, and also concerning the orientation of the particle during the falling through the atmosphere. Another parameter is the specific differential phase, KDP. And this parameter gives you information concerning the shape also of the particle, but also concerning the water content and the mean drop size. And the last one is the correlation coefficient. And it will give you information concerning the mixture, the melting process, and the canting angle. And this coefficient, the ρHV, is a strong signature of the melting layer, what we call in radar the bright band, and it will help you to analyze the altitude of the 0-degree temperature. So X-band radar, it's very sensitive to attenuation, and here you have a raw image of a precipitation in Niger in 2010. And what you can see here, I don't know if you can see my cursor, yeah? So what you can see in the middle of the images, okay, here, where is my arrow? This is the center of the image, and this is the place of the, oh, I've lost my, this is the place where is located the radar. And here, what you can see is very high reflectivities around 45 to 50 dBz. And this is the signature of storm cells, very high intensity of rainfall. So this high reflectivity produces a big attenuation, and at the back of these cells, the signal is totally attenuated. So with the polarimetric parameter, we can have access to a specific algorithm, Z-phi. And when you apply this algorithm to your data attenuated, you are able to retrieve the corrected reflectivity. And as you can see, the level of reflectivity is higher, and also in the part where there is a strong attenuation, now we have strong reflectivities. So this is important to correct the images before to compute the estimation of rainfall. And with these corrected images, we can apply different kind of relationship to try to get the accurate estimation of rainfall. So here you have 4 different relationships. This one is directly a relation between the reflectivity and the intensity of rain. The next one is a relation between the specific differential phase and the intensity of precipitation. Here, you've got a relation directly with a relation between the attenuation of the signal and the intensity of the rain. And the last one mix different kind of parameter, the horizontal reflectivity, the differential reflectivity, and the specific differential phase, to compute the rain intensity. And as you can see here, for full season, it's the season 2013. We get in Burkina Faso in West Africa with very strong rain. The best method seems to be the one with RKDP, and this is due to the fact that the KDP is not affected by the attenuation. That means even if you have strong attenuation, you are not subject to a bias when you use this relationship. So the relation is quite good because you can see we have a correlation up to 77% with a low bias. And also for the relationship with the attenuation inside is not so bad. We have different relations that we can use with a limitation of error. So one thing we should to address if you want to make accurate measurement of rain is what we call the drop size distribution, we used to call that DSD. And it is very important because most of the parameters linked to the rainfall are what we call the moment of the DSD. That means it's a power law of the diameter multiplied by the concentration of particles at this diameter. And it's the case, for example, here I give you two examples. It's for the intensity of rain, but also for the reflectivity. And it's for that you are able to combine these two relationships to provide a new relation that give you the rain intensity in terms of reflectivity. So to get information concerning the DSD, you can use a spectroproviometer. This is an images of Parsival 2 from the company OTT. And this sensor, in fact, it's a laser going from a transmitter to a receptor. And when the drop falls inside the laser beam, there is an attenuation of the power received at the reception part. And with this information, you can compute the size, the diameter of the particle, and the speed of this particle. And collecting many information during time, you will get diameter and speed spectrum, and it's going to be like that. With for a few diameters, you got the concentration of particles. And after a while, when you have enough information, you can try to modelize this spectrum with, in this case, we use a gamma model. It's something very common. And what you will get is a climatologic parameter for a specific type of rain or a specific region. And I think you cannot take a relationship from one region and try to do the same in another region if the rain is different and if the climate is totally different. So one limitation of the export radar has all the different kind of X-band radar. When you put this kind of radar in the very strong rain, is that when the intensity of the rain is too important, then that means you can get extension of the signal just behind the strongest cells. And the worst is when you get the storm just over the radar, you can get a full attenuation of the signal. But as soon as the storm crosses the radar, you can discover all the cells here in the orange and the yellow color, and you discover behind the stratiform region of the storm, and then you can compute for all the rest of the time the accurate quantitative estimation of precipitation. So to conclude this part, the question I tried to address was it the efficiency of an X-band polarimetric radar to produce rainfall fields at fine spatial and temporal scale? What I just mentioned is if you use a single polarization radar, just to remind you that the Marshall-Palmer relationship is not suitable for all the type of rain, and there is a strong attenuation to compensate. And this is true for the two kind of radar, single and dual polarization. The local and regional DSD must be accurately documented. And this could be solved by using a spectral preview meter, and it could be something interesting to install in the roof of the car. With a dual polarization radar, we have different relationship based on the polarimetric variable, which can estimate accurately the rain rate, and the AKDP is not affected by rain, and it seems to be the best relationship to measure the rain intensity. But also, we have a tool to correct the attenuation using the Ziphy algorithm. So a radar like export could be a way to validate accurate measurement of rain if we can bring it to Vietnam. So we're going to continue with the second part of this webinar. Is concerned flood risk and alert, and the question addressed is what is the potential of mobile phone network for precipitation estimation, and how can this information be used in an early warning system of flood? So we try to, in fact, we're going to try to transform a commercial telecommunication link into a rain gauge. So in this schematic, you can see a transmitter and a receiver. This is a common communication link. That means it's not the link you get between your cell phone with a pylon with an antenna, but it's a communication between antenna to antenna to bring the signal to the technical center of the company. So it's not directly linked with your phone, but is a step after. When you have reached the first pylon, then your voice is propagating through a pylon to pylon with this kind of link. So in fact, rain disrupts signal transmitted on mobile telecommunication network. And this is due by the fact raindrops absorb and diffuse some of the energy transported by the wave, by the electronic wave. As we can see here, you have this is represent the amplitude of the signal, and then when we start to cross the shower, the power starts to decrease up to the end of the shower, and then you arrive to the receiver. The fact is, the equipment of the telecommunication tower are able to record this information of power transmitted and power received, and then you can get the information of the variation of the signal in real time. So this is something not very new. Early in the 70s, Atlas and Ulbricht have presented a paper with a link between the mean intensity of the rain between the two pylons as a power law, and multiplied by the distance between the two pylons could be related to the attenuation of the signal. And these two parameters, C and D, are dependent of the frequency, but also drop size distribution. We talked just before about the drop size distribution, and also to the temperature. What we should keep in mind, and this is very important, is the fact that, for the same average rainfall intensity, the bigger is the distance L, the bigger is the intensity, and also the higher is the frequency, the bigger is the intensity. So in fact, if you use a frequency close to 7 gigahertz, you will need a longer link to detect the attenuation of the signal. But if you use a link up to with a frequency of around 40 gigahertz, you can get information of very short distance, like a few kilometers, 1 kilometer or something around. So a few years later, by the 2006 and 2007, two teams, one in Israel and one in Netherlands, have made the demonstration that the commercial link could be used to estimate the rain. And this is the beginning of our story, because after that, they propose to use the technique in 2D, and Overin started to show that he could make accurate measurement of rain in Rotterdam and also in all the country in Netherlands. And he compares this result with radar calibrated with rain gauges. So we would like to know if this technique could be used to complement measurement network where is needed. And in our case, we would like in the beginning, early in 2010, to see if this technique could be used in Africa, where the information of the rain is very important. So we get an agreement with a company in Burkina Faso. It's Telecel, and this company started to provide us some information of transmitted and received power. And this is an image of what we get as information. So in this graph, you can see on the top the dates. So we have 6 days of information. And here you have the power. So it's is going to be between 0 to minus something. And what you can see here in green and in red, this is the vertical polarization of the link, and it's also the horizontal polarization of the link. So sometimes it's happened, like you can see in this image, you can get 2 antenna. In fact, for security reason, you have 2 links, one in horizontal, another one in vertical. In case of if there is any problem, you always have one link working, and you can have a continuous information coming to the technical center. So if you have a look to this curve, you can see sometimes a strong attenuation of the signal, a strong disturbance of the signal, and this is a signature of rainfall, because as I mentioned previously, the rainfall attenuate the power of the transmitted signal. So the information registered at the receiver antenna could show you that something is happening here. And as you can see, there is very similar attenuation between the vertical and the horizontal polarization. So that means there is the same phenomena producing this attenuation. And also here is exactly the same. But one of the difficulty of treatment is you have also fluctuation of the signal, even if there is no rain. So we have to deal with that if we want to produce accurate rainfall estimation. So it's what we did for one season in 2012 over Burkina Faso. We compare one link with one rain gauge. And you can see the results here for the full rainy season. So here you have the beginning, 1st of July to the end of August. And here, this is the accumulated rain along the season. So in dash point, you can see here the results obtained, the measurement of the rain gauge. And in the black line, this is the estimate rain with the link with our method. And what you can see, we have a very similar estimation of the rain over the season. It's a correlation, it's 0.81 with a very low bias of 7.5%. And we've put a cross here, a black cross, when there is no detection of the rain. That means we are not able to see enough attenuation to detect the rain measured by the rain gauge. And sometimes, only one time, we get what we call false alarm. That means we had an attenuation that we link to the rain, but we didn't observe rain at the rain gauge. So we can say that we have a very good agreement between the estimated and the measured accumulation of rain at the link and at the rain gauge. The correlation is about 80%. The bias is low, and the probability of detection is around 95%. So after this proof of concept for one day, one link only, we did the same for in different regions. And with agreement with telecom company, we were able since now 3 years to collect in real time information concerning the attenuation of the links over the Niamey. Niamey is the capital of Niger in West Africa. So all the red links here are the equipment of the Orange company over Niamey. And as you can see here on the different images, at one moment, you can see attenuation on the corner upper left of the image. This is a sail coming over the city and moving through the city and disappearing. And we do the same also in Douala in Cameroon, and we get the same results. Sorry. So this thing is working now for 3 days, and we are collecting every 15 minutes attenuation, signal attenuation from different link, and we are able to produce accurate measurement of rain with this technique. We talked at the beginning of my presentation about a project. The project was Rainfall app Bamako. So it's the one funding by the World Bank and the Korean Fund. And we try to make for this project a demonstrator of early warning flood system for Bamako. Bamako is the capital of Mali. And the design of the system was to collect information of what we call the backhaul. So the backhaul is all the antenna of an operator. All this, the information could be concentrated to the technical center of the operator. In this case, this is Orange. And all the information is sent by an internet link to our server. And also, we have a network of rain gauges in real time transmitting by 4G information of rain. So with these two information, we compute the spatial rain estimation, rainfall accumulation, and with a rain runoff model, we compute map of runoff and map of early warning information, and all this information are sent in real time to the different services in charge of the flood alert and the protection of population. That means Met Office, civil protection, municipality authorities, regional governor, and also colleagues, scientists in Bamako and also in France. The thing is, now, since 5 years, we are trying to get information with the Orange company. We are stuck for a technical reason. In this case, as we can do the same with Orange company in other countries, we have trouble with Mali to obtain this information. So the link, the internet link with the attenuated information is not working, but we are still in progress. So we have more than 13 rain gauges over Bamako, and we are able to produce less accurate information, but we are able to run the demonstrator and to transmit information in real time to the service in charge of the floods. But if we can have all the links over Bamako in the next day, they promise me to give me access to this information by the end of the month. We will get a very strong, accurate measure of rainfall, and we can produce runoff map and the early warning map very precise. So for conclude this part, the question addressed was what is the potential of mobile phone networks to precipitation estimation, and how can this information be used in early warning system of flood? We have made a proof of concept on one leak for carried out for the first time in Africa as a part of the Rainfall project. And when we publish our result, we will award by France. We are now, since few years, able to monitor rainfall over 2 capitals in West Africa, and this in real time. And we can say that using microwave commercial link to measure rainfall is an innovative and green solution, because you don't have to install equipment. You just have to collect information directly from the technical center of the company. Few limitation is the difficulty to obtain data from commercial telecommunication company. Even if most of the time they think your project is very interesting and very useful, they are here to provide money, not to share data. It's a shame, but it's like that. And also one difficulty is to solve the problem of what we call the wet antenna. It's attenuation directly on the antenna caused by the thin cover of water you can get during the rain, and this may cause bias, and this issue should be addressed very carefully. So in the general conclusion, as I present you, as an engineer, I have developed an X-band polarimetric radar that can be easily deployed to address research questions. Polarimetric radar are useful tool to estimate precipitation and to make an accurate documentation in spatial and temporal variability. Specific focus should be put on the knowledge of the drop size distribution when you install the radar in the specific area. And we should keep in mind that intense rainfall may cause signal attenuation or extinction. And that means you have to decide to place the radar in the correct place if you want to protect an area, for example. As a scientist, I have provided some element of knowledge concerning the estimation, the quantitative estimation of precipitation using weather radar. I have tested successfully an innovative method of precipitation estimation based on the commercial microwave links. And this method could complement an existing measurement device for low cost. And this method can be used to elaborate a flood early warning system. So as a prospect, as you know better than me, flooding is a major issue of Ho Chi Minh town. The objective of my webinar was to propose my expertise to address the question of the influence of spatial and temporal rainfall distribution in flooding over Ho Chi Minh town and the Mekong Delta region. This part of Vietnam is a perfect place to study monsoon phenomena, because you have also urban and rural area, and also many colleagues at CARE and at the Ho Chi Minh Technology of University, and also in other institutes and universities, study water in city and in rural area in terms of pollution, coastal erosion, and water resource. And also the information of rain could be of interest for the comprehension of the black carbon in the atmosphere. So I will probably get the opportunity to come to CARE to visit you 2 months in 2022. I would like to propose you to install a spectropolarimeter to start the documentation of the DSD at Ho Chi Minh, and also to spend this time to develop a research project with colleagues concerned with this issue. And also we can discuss of the suitability of my assignment to the CARE by IRD and the possibility to deploy the export radar for some years in Vietnam. So on my next slide, I won't try to say anything, only I very thank you for your attention, and I give you the floor if you have any question. Thank you very much.
Thank you very much, Frédéric. So maybe Zan or Duke, as a director of CARE, you could introduce the question session, please.
Dick, yes. Do you have any question for Frederick talk? Any question?